Space is vast. We measure its distances in light years, the time it takes for light to traverse the cosmos. Yet, on Earth we have machines that hold the universe in a box. These are analog computers, using physics to unravel secrets. Imagine a child's seesaw, perfectly balanced. Push one side down, the other rises. This embodies analog computing. Instead of ones and zeros, they use physical quantities. These machines are sculpted to solve equations. They remind us the universe can be our calculator. Let's explore the world of analog computing. The world around us is a symphony of continuous change. Temperatures rise and fall in gentle waves. The hands of a clock sweep through time in an unbroken circle. This is the language of nature, a language spoken fluently by analog computers. Unlike their digital counterparts that break data into discrete bits, like the individual frames of a movie, analog computers embrace the smooth flow of reality. They use continuous physical quantities to represent data. A voltage might represent the altitude of an airplane. A current could stand for the speed of a flowing river. Imagine a dimmer switch controlling a light. The light doesn't just jump between on and off. It brightens and dims smoothly, mirroring the continuous change in the switch's position. This is the essence of continuous representation in analog computing. Furthermore, analog computers often employ physical models that directly mimic the systems they're designed to analyze. Need to understand the flow of water in a dam? Build an analog computer that uses actual water flowing through scaled-down channels. This direct, tangible connection to the physical world is a hallmark of analog computing. Long before silicon chips, our ancestors harnessed analog computing. The Antikythera mechanism, an ancient Greek device, is a testament to their ingenuity. This intricate system of gears tracked celestial bodies with remarkable accuracy. In the 20th century, the differential analyzer solved differential equations. These machines were instrumental in fields like ballistics and bridge design. The harmonic analyzer decomposed complex waveforms into fundamental frequencies. This advanced fields like acoustics and signal processing. The tide predictor forecasted tides, vital for navigation. These marvels highlight the ingenuity of analog computing. Sculpting solutions. The art of setting up and reading analog computers. Imagine an artist meticulously shaping clay to create a sculpture. This is akin to setting up an analog computer. It's a process of carefully connecting components, adjusting parameters, and molding the machine to embody the problem at hand. Let's take the example of a simple analog computer designed to calculate the area of a rectangle. This machine might use two potentiometers, variable resistors, whose resistance changes with rotation, to represent the length and width of the rectangle. The voltage across each potentiometer would then correspond to the length and width. These voltages would then be fed into a circuit designed to multiply them, essentially mimicking the mathematical operation of length times width. The output voltage of this circuit would represent the area of the rectangle. Reading the results of an analog computer is like interpreting a finely crafted instrument. Instead of displaying numbers on a screen, the answer is encoded in the continuous output of the system. This might be a voltage read on a voltmeter, a needle pointing to a value on a dial, or even the position of a mechanical component. A dance of strengths and weaknesses, weighing the pros and cons of analog. Analog computers, like all inventions, come with their own set of strengths and weaknesses. One of their biggest advantages is their inherent speed. Since they operate on continuous physical quantities, they can perform calculations at speeds often exceeding those of digital computers, especially for complex simulations. Furthermore, their direct connection to the physical world makes them ideal for real-time control systems. Think of the autopilot in an aircraft, constantly adjusting control surfaces to maintain a steady flight path. Analog systems excel in these situations. However, analog computers are not without their limitations. One major drawback is their susceptibility to noise and inaccuracies. Real-world physical quantities are rarely perfectly clean and stable. Small fluctuations in voltage, temperature, or mechanical tolerances can introduce errors into the calculations. Another limitation is their lack of flexibility. While digital computers can be reprogrammed with ease to tackle a wide range of tasks, analog computers are often purpose-built for specific applications. Changing their function might require physically modifying the hardware. Bridging the divide, the rise of hybrid computing systems. In the world of computing, the lines between analog and digital are not always clearly defined. Hybrid systems, as their name suggests, combine the strengths of both approaches, leveraging the speed and efficiency of analog computation for certain tasks, while relying on the flexibility and accuracy of digital systems for others. Imagine a hybrid computer designed to control a robotic arm. The analog component might handle the real-time calculations for smooth, precise movements, while the digital part could manage the overall task planning and decision-making. These hybrid systems are becoming increasingly prevalent in areas like signal processing, control systems, and even artificial intelligence, offering the best of both worlds. Analog in the digital age, a resurgence of the Forgotten Powerhouse. In our modern world, dominated by digital technology, it's easy to dismiss analog computing as a relic of the past. However, the unique capabilities of analog systems are experiencing a resurgence of interest, particularly in niche applications where their speed, efficiency, and direct connection to the physical world offer distinct advantages. Researchers are exploring the use of analog computers in areas like drug discovery, material science, and even artificial intelligence. The development of new materials and fabrication techniques is opening up new possibilities for creating smaller, more efficient, and more versatile analog systems. The story of analog computing is far from over. It's a story of human ingenuity, of finding elegant solutions by harnessing the very laws of physics. And as we continue to push the boundaries of technology, who knows what new chapters await us in the fascinating world of analog computation. Please subscribe.